Okay, off we go. Attendance quiz, attendance code, all that, don't forget. Picking up where we were last Wednesday, of course. So we were talking about how to parameterize a curve going the sort of, if you will, the wrong direction on the unit circle. And we talked about two different ways to do that. And I'm not going to repeat all that stuff, but the point is, once you have that parameterization, then you can take these parameterizations, and plug them into our usual formula and yada, 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 calculation, and get an answer for how to compute the work when you're going the opposite direction along that curve. So those are the first two methods I was going to show you for how to answer this question. How do you compute the amount of work if you're going clockwise instead of counterclockwise? Here's the third way to do it. Much better. Much better. And that is to say, look, we already know that along the original curve, the amount of work is pi. We've already done that calculation, right? So the curve that I've been asked to deal with is just the same curve oriented in the opposite direction. And of course, orienting in the opposite direction gives you a minus sign. So if you want to know the integral over this second curve, oriented clockwise instead of counterclockwise, it's just the negative of what we already computed, and therefore, altogether, negative pi. Done. Right? So much easier. Right? We don't have to sort of redo an entire calculation from a parameterization. The curve we are given, same as the previous. The only difference is the orientation, and we know from last time that a change in orientation just leads to a minus sign in the computation of the vector line integral. So this is by far the best way to do it in the context that, of course, given that we'd already done that green calculation there for the counterclockwise. Okay, so that's the way to go, I would suggest. Now let me show you a fourth air quotes way to do it. I don't really approve of this fourth way. I'm showing you just to be clear about what I don't want you to do, and that is to make what I like to call a time travel argument. It is very, very fishy, and the idea is to say, well, we've parameterized counterclockwise. If you want to go clockwise instead, then it's like you're starting at pi and ending at 0. In other words, just switching the bounds on the integral. Right, now this is very tempting. Kind of seems like it sort of makes sense. And of course, now we know from single variable calculus that when you switch the bounds, that indeed does give you a minus sign. And yes, it is indeed the same minus sign that we see there. You will get the right answer. And of course, y'all have heard me say it a bunch of times. It's not about the answer, it's about the argument. We need to think about the argument. Does this argument make sense? And here's the problem with the argument. The calculations we've been doing are set up based on this framework that we have. Right? We've put together various relationships between various objects, and the R and the R prime and the T and the DR and lots of details. Right? When you go backwards through an existing parameterization, those relationships are not all still true. So, for example, here's an easy one to notice: no longer true. If you use the same parameterization but just switch your bounds. Same parameterization means that R prime has not changed. R prime is still pointing counterclockwise. But your velocity is not. Your actual velocity, because you switch the bounds, right? Your actual velocity is clockwise. You are, in fact, actually going clockwise. So these are not the same anymore. And likewise, similar thing here. These are not the same anymore either. So what you're saying when you write this down, right, is you are saying, hey, I'm going to use that existing sort of framework of ideas that we've set up, but that's not all true anymore, right? Now, can this be fixed? Yeah, sure, it can. This can all be fixed. but it would have to be fixed, right? And until you have fleshed out all of this stuff, at best your argument is unclear. Right? I don't know what you are thinking. How much of the argument that you're portraying do you actually understand, and have you actually thought through the related detailed levels of? Right? So at best it's unclear. So now what's to be gained from this, right? Why would we want to go to the trouble? Why would we want to maintain the ability to make such an argument? And I'm going to propose there's not much of a need for this. The reason why is because we already have this argument, right? We already know that opposite orientation introduces a minus sign. I don't need this argument here. That would be confusing. And, again, a whole different framework to have to set up, and all completely unnecessary. This is just as easy, right? And doesn't have the clarity problems and confusion problems that what I like to humorously call time travel arguments kind of have. Okay. All right. Yeah, question?
I just don't get it why one thing is different than the other, and why one would be unclear and the other would be clear.
Yeah, because we made an argument, and I've given you all an explicit theorem here about what happens when you change orientation, right? So opposite orientations introduce a minus sign, and we argued why that was true, because when you go in the opposite direction, all of your DRs are literally exactly negatives of what they had been. So there's a nice simple argument, and we have a theorem to that effect. Right? So that's why this argument here is good for that reason. Now, yes, we could go through and redo sort of everything with all the various players and reevaluate all of those relationships and stuff. We could do that, and we could make this make sense. But it's a lot to do, and it just seems like way more trouble than it's worth. Right? So again, it's not that it can't be done. It's that we're not going to do it, and unless you do it on the exam, I have no evidence that you know what you mean when you write that down. Does that make sense? Yeah. So you got to keep in mind, it's about the argument, and in particular, what can I infer? What can I confidently infer that you understand based on what you've read? So that's the sort of the little detail devil that makes it a problem. Yeah. Okay. Next question. We've talked about vector line integrals. We've talked about vector line integrals specifically when the vector field represents forces. And we wrote down the vector line integral in the context of the vector field representing forces in an attempt to compute work. So this is what we've done so far. Right? We have a motivating application. How do I compute work? And the answer was this new construction called the vector line integral. And so new question, what if my vector field here, what if it represents a fluid flow, not a force? What now does this represent? And it can't be work. Definitely not work, because there's no force in the story anymore. Right now we're looking at we got an integral and there's a vector field, but the vector field represents something that's not a force. No force, no work. So how should I think about this in this new context when I'm thinking about fluid flows? So the answer to this question is a little bit weird. It's something unfamiliar. It's something for which we don't currently have a term. So there's going to be something a little unsatisfying about the answer. So keep that in mind, and apologies in advance for the dissatisfaction of how we're going to end this. But we will still end up with what I think is a reasonable interpretation. Here's how I like to approach it. Suppose we have a curve, and I'm going to imagine that we look at a cross-section of area like that, and that we consider the corresponding little thin region kind of around the curve as created by that cross-sectional area. So it's almost like it's a little tube, right? It's not actually a confined tube, right? But it's in the shape of like a sort of a bent rod, maybe, possibly. Okay, so keeping in mind our vector field represents a fluid flow, so there's a bunch of fluid flowing around. Let's talk about the fluid that's in this little yellow tube-like region. And of all of that fluid, I want to ask kind of a strange question. I want to ask, what is the total rate that fluid is flowing along the curve? Again, weird thing to want to ask. Why would I want to ask this question? Not at all clear, but play along with me if you will, and we'll get a nice punchline. Okay, so here we go. Total rate that the fluid's flowing along the curve. Well, look, we've got a certain amount of fluid. There's a little piece of the fluid. If I look at one little piece of the curve, this is the corresponding amount of that fluid. And here's how much fluid it is. Area times thickness. That's how much fluid there is. We've got a flow, of course. That little piece of fluid maybe is going like so. That's not what we're interested in. We're interested in the component that suggests how much it's flowing along the curve. I only want to know about the extent to which that flow is along the curve. I want to throw away, ignore the extent to which it's flowing perpendicular to the curve. I don't care about that. I'm just interested in just the extent to which it's flowing along the curve. And, well, we know how to compute components. Right? Components are dot products with unit vectors. And in particular, if you want to go along the curve, the unit vector is the unit tangent vector. So there you go. I mean, it's a pretty straightforward little thing to write down. Having done that, I can then say, okay, well, this whole thing, dq, you know, I kind of break it up into pieces here, but there's my whole dq. And again, factoring out the a, and then you notice that we end up with this expression, which we've seen previously. That is one of our alternative notations for a vector line integral. And so now I'm just going to replace that with my sort of personal preferred notation for the vector line integral. A little bit more compact, a little bit more, to me anyway, a little bit more relatable. And there you go. So altogether, the answer to the question, what is the total rate that the fluid is flowing along the curve? Weird question though that is. The answer is area times the line integral. Now quick pause. Oh yeah, go ahead.
How is this different from flux?
So flux, yeah, so what we've talked about previously with flux is that you have a surface and you're interested in how much the fluid is flowing through the surface. Right? So here we don't have a surface, here we only have a curve, and you're right, I'm not going through the curve. I'm not interested in fluid flowing through the curve, I'm interested in fluid flowing along the curve. Yeah. Does that make sense?
Yeah.
Okay, so there's a part of this answer to this question that I'm going to say is kind of expected. And it's the part about the area. So I'm going to propose that, well, of course, as follows, keeping in mind this cross-sectional area, the more area you have, the more fluid there is under consideration, and the more fluid you got, the more fluid you've got flowing along the curve, right? So in some sense, it's not particularly surprising that the answer is proportional to area. I'm going to call that kind of expected. And so I'm going to rephrase the question now to, instead of how much is the fluid flowing along the curve, I'm going to say how much per unit area. Of course, it's proportional to area. When something is, of course, proportional to area, it makes sense to kind of factor that out. And let's talk about how much per unit area. And so per unit area, if you think about it, again, taking this, dividing it over here, per unit area, the answer is the line integral. And that's what I've got stated right here. The line integral itself, by itself, just the line integral, says how much is fluid flowing along the curve per unit area, of course. Does that make sense? Any questions about that? Yeah.
Kind of similar to this question. Is there like some relation between this and flux? Maybe like knowing one, like you could figure out that.
The problem is that they're about different things, right? So flux requires that we have a fluid flow, right? Same fluid flow kind of a thing. But flux requires that we have a surface, and we're interested in how much it's flowing through the surface. So here we don't have a surface. Here we just have a curve, and there isn't a single direction through a curve. There's a lot of directions, arguably, that are kind of through a curve. You know what I mean?
Okay. But
there's only one direction along the curve.
So this is only for curves?
This is only for curves. That's right. That's right. Okay. Okay, so this is the take. Now keep in mind, our original goal was to try to figure out, hey, how should I think about vector line integrals in the context of a fluid flow? And here's our answer. The answer is, if you're interested in a line integral in the context of fluid flows, the line integral per unit area, yeah, of course. But the line integral tells you how much the fluid is flowing along the curve. And this is not something that we have a name for previously. So it kind of seems a little anticlimactic. We don't get that conclusive sort of the answer is work, or the answer is, some other single word name that we're already familiar with. But this is how to think about the line integral in that context. Okay, now there is a special case that we do have a name for. Very useful. And that is to think about the special case when the curve is a closed curve. And a closed curve that says that that curve starts and ends at the same point. So for example, this curve right here is a closed curve because I started and then I went around and then I ended exactly where I started. Is that cool? Everybody with me? Okay, so in that case, given some vector field, and I'm imagining this vector field that I've got drawn here. For example, we want to ask the question, what does the line integral represent? Well, we already kind of know. The line integral says, hey, to what extent is the fluid flowing along the curve? And let's just kind of look one little piece at a time. Let's look at this little piece of curve right here on this little piece of curve. To what extent is the fluid flowing along the curve? I would say quite a bit. It's flowing exactly, my intention with the drawing anyway, was that it was going exactly the same direction as the curve. The fluid is flowing as much as possible totally along the curve. And likewise, everywhere along the curve. If you come over to here, again, same deal. The curve is going that way. The fluid is also going that way. The fluid is very much so flowing along the curve. And so we would expect this line integral to be positive. And I'm going to say this is a pretty good picture to motivate this terminology that we would call this circulation. And if you think about it, this curve going around in a circle, right? And coincidentally, I've drawn it here as a circle, but in any case, if you look at the unit tangent vector, right? I've got these unit tangent vectors going along the curve. Those unit tangent vectors will literally go all the way around the unit circle. That literally the unit tangent vector makes a loop, right? So if this line integral represents the extent to which the fluid is doing what the curve is doing, and if the curve is going around in a circle, I think it's reasonable to say that we are arguing here that the fluid is kind of going around in a circle. and thus the term circulation. There's just a terminology thing, right? But I think that's a reasonable sort of intuition for that terminology. Yeah.
Just to make sure,
Yeah.
for the circulation,
Yeah.
If it's counterclockwise, it's not like positive is counterclockwise.
You ask a great question, and I'm going to totally elaborate on that. Yeah, just give me a second to build up to it. Yeah. Okay, before we go on, a great natural question to ask next, but for this first example, is everybody with me? Reasonable intuition? Okay. All right, so let's look at the next example here. The next example I'm going to look at, you'll notice the exact same vector field. Exact same, I'm not going to go all the way around, it takes too long to color that all in. But exact same vector field. And now we're going to look, though, at this different curve. This curve now going around this way. And now let's think it through again. And again, same vector field, green here. To what extent is the fluid flowing along the curve? You know, that's what a vector line integral represents. And, well, is the fluid flowing along the curve? Kind of, right? But the curve is going that way, and the fluid is going the other way. It's literally going the opposite, which I think it would be reasonable to call that a negative, right? So the fluid is going backwards compared to the direction of the curve, and you can look at, on each little piece, those dot products are going to be negative because, well, their vectors are going opposite directions. And so your circulation here would be negative. So now a confusing thing here, and what a lot of students get tripped up on is, well, wait a minute, it's the same fluid. How come in one of these calculations we conclude that fluid is circulating positively, and with the other one we conclude that it's circulating negatively? And this is kind of to your question. The answer is, you got to keep in mind that when we say the word circulation, it's always circulation relative to the curve that you're measuring the fluid against, right? And so intrinsically, when we did this first calculation over here and got positive circulation, it was with the understanding, it was with the understanding that we're defining counterclockwise as the positive direction, because that's the direction of the curve that we're comparing f against. So you might say that this integral asks the question, to what extent is this fluid flowing counterclockwise? And the answer is a positive extent that this fluid is flowing counterclockwise. And then you might interpret this question here. Wrong color. Hang on. When we're doing the integral for this curve, and we ask, hey, what is this circulation? And we got negative. The question that we're asking is, per this curve, we're asking, to what extent is this green fluid flowing clockwise? To what extent is it circulating clockwise? Because the curve is clockwise. And if you ask, again, this green fluid, to what extent is that green fluid circulating clockwise? Well, it's not flowing clockwise. It's flowing counterclockwise. Still counterclockwise, but now negative because we're comparing against clockwise. Does that make sense? Everybody happy with that? So, which one of these is right and which one of these is wrong? Is clockwise the right one, or is counterclockwise the right one? A very important answer to that question is neither. And these are both equally reasonable questions to ask. Now, there is a very closely related concept that we're going to talk about on Wednesday that we're not going to have time to get to today. And on Wednesday, there will be one of the, there's again, not this idea exactly, but a closely related idea. One of these will be preferred over the other. But in this context, as we have things defined, neither one of these is right and neither one of these is wrong. They're just arbitrary different. Okay. A real quick observation. Here's another curve, sort of off-centered, if you will. And what's the circulation here? Is the circulation positive or negative? And this one gets weird because sort of on the left side, if you will, the fluid is flowing opposite of the direction of the curve. But on the right side, if you will, it's flowing in the direction of the curve. So it's like you've got some plus and some minus, and there's a little tug of war between the plus and the minus, and it's not clear which one is going to win that tug of war. You can kind of speculate based on what the arrows look like and try to make a case for yourself, and you can probably even guess the right answer. But there's a much better way to think about this. Again, we're going to have available to us on Wednesday. So for the moment, I'm going to leave this as it's not clear, and we'll come back and reevaluate later. Okay, last thing I want to point out, if you were to have some small object, and I like to think of a leaf, especially this being the fall, right? Fall color there, leaves falling off of trees onto the surfaces of, little rivers and creeks and stuff around here. And if you see a leaf floating on the river, on a creek, right? And if the water is doing this, like so, well, the water is going around counterclockwise. Reasonable speculation, I think the leaf is going to rotate also counterclockwise. What do you think? So can you buy it? I don't know if you all have ever done this in, various different contexts, hiking route in the woods or whatever. You come across a little stream, and sometimes you see a little whirlpool, little eddy current, you know what I'm talking about? I don't know if you've seen this. Another context is if you take a bath and you drain the tub, it tends to go down with a sort of a whirlpool, kind of a, what's the word? It's not typhoon, but what? Anyway, the water does like this, right? You can take any little small lightweight thing and just kind of drop it right where that is happening, and you'll see that thing rotate also. Stuff that's floating in a fluid tends to do what the fluid is doing. Right? So I think another nice way to think about circulation is that the circulation, by virtue of its being positive or negative, and again, all relative to the curve that you're comparing it against, circulation is a suggestion of how that small object is going to get rotated by the fluid. And circulation counterclockwise would suggest that the little floating thing would also rotate counterclockwise. Does that seem reasonable? Okay. All right. Okay. Couple of neat little bits here. There are some cool opportunities to save yourself a bunch of trouble. I encourage y'all to be head on a swivel, always looking out for these. You may recall I'm constantly pitching the idea of pay attention to symmetry, right? Very often, surprisingly often, you can save yourself loads of trouble of computing an integral by just observing, oh my gosh, well, it's zero by symmetry. Walk away. So this is a different kind of awesome. We'll start off by observing that I'm given a curve. Now, I have to clarify that I've abused the term parameterization here. I have given spherical position as a function of time. A parameterization, you can look back and check the notes, a parameterization gives rectangular position, x, y, z, as functions of time. So when I say this is a parameterization, what I mean is this implies a parameterization, because let's face it, if you know rho phi theta, you plug into the conversion formulas, now you've got x, y, z as functions of t. And they'd be super ugly functions of t. And you might amuse yourself by writing those down and then just stand back and, in awe of how extremely inconvenient that parameterization would be. It's a terrible, terrible parameterization. Okay. All right, but the key point you'll notice is that, weird though this is, this entire parameterization takes place with rho always equaling 1, which means you are always entirely confined to the surface of the unit sphere, where rho equals 1. Right? So this is a weird curve, and it's doing all kinds of crazy nonsense on the surface of the sphere, but it is always, and fairly clearly, always on the surface of the sphere. And because it's always on the surface of the sphere, I'll point out that dr, your differential, is therefore always parallel to the sphere. It's tangent to the sphere. Like if you're moving along a surface, your velocity is tangent to the surface. That's a geometric appeal. Does everybody believe that? Right? If I'm moving around on the surface of this table, I could be doing all kinds of weird things on the surface of the table, but my velocity is always tangent to the table. Okay. All right. Now let's look at our vector field here. Let's see, we've got this vector field given. That's kind of weird. What are we going to do about that? Well, that vector field, check it out, is always a scalar multiple, right? X squared y is it's a function of position, but it's a scalar, always the same scalar. Scalar multiple of the position vector. And now another geometric appeal, and this is just a curious feature of spheres. Correction, spheres centered at the origin. You just got to take a moment to think about this, right? Consult your sort of geometric intuition. A sphere centered at the origin has the feature that these position vectors will always be perpendicular to the surface. In fact, this is a peculiarity exclusive to spheres centered at the origin, that the position vector is always perpendicular to the surface. What do you think about that? Is everybody buying that? Okay. So, just as a for example, here we are on the surface of the Earth, and let's call it a sphere. Close enough. Gravity is always toward the center. Gravity is always in a direction that's perpendicular to the flat ground. And again, that's a feature peculiar to spheres. Okay, so here's the thing. If R is always perpendicular to the sphere, then that means that the vector field also is always perpendicular to the sphere. And now let's look at these two facts together. Let me get rid of that. Let me get rid of that. In fact, I don't even really need that anymore. I've got F and I've got dr. Dr is always parallel to the surface. F is always perpendicular to the surface. And that means that these two vectors are always perpendicular to each other, or at least they're always orthogonal to each other. That means that this dot product is always 0 because they're orthogonal. And that means that my integral is 0. Didn't have to deal with that nasty parameterization, didn't have to pull back through anything, didn't have to compute the velocity, didn't have to do any single variable calculus. Geometric observations. What do you think? Everybody see the value of this kind of trick? Right? Now again, how often does stuff like this happen? You'd be surprised. This actually happens fairly often. Because when you're doing engineering, y'all are largely engineers, right? I understand. Physics or engineering, very often you're dealing with natural things. Natural things very often are spheres and other geometrically natural and simple and basic kind of shapes. So this kind of thing is not that rare. And I saw it come up a million times. I don't know. I'm not prepared to give a percentage. I estimated that odd symmetry arguments were 20% of the integrals that I saw as a physics major way back when. I don't know what the number would be for this. It might be 5 to 10% maybe. That's still a lot, right? And it's definitely worth keeping an eye open. So please, always head on a swivel. Always look for these kind of opportunities. Reminder, they do not announce themselves for you, right? So you have to be on the lookout. And for example, here, the big, leaps off the page at me anyway, that's a big one. I look at that and I think, wow, okay, sphere. Yeah, spheres are awesome. I should be thinking carefully about the geometric niceness of a sphere, various different cool facts. And then, of course, this, right? The fact that I'm looking at a scalar multiple of position, that leaps off the page at me as well. So when you see stuff like that, start looking around for possible clever arguments like this. Okay. Next thing. This is mostly just notation. We already know this fact about the dr vector. Dr is r prime dt. Well, of course it is. The derivative is done one coordinate at a time, so I can break down r prime in coordinates. I can distribute the dt. Kind of makes sense that x prime dt I would rewrite as dx. Likewise dy and dz. And check it out. What we've got here then is what we have is a coordinate representation of our vector differential dr. And so I will just take this dr and just rewrite it like so. It's just notation. Now your vector field, of course, will have coordinates. PQR is actually a pretty common choice to name those coordinates for whatever reason. It's just I wouldn't even call it a convention, but it's a common choice. And now, check it out, my f.dr, again, this is my favorite notation for writing vector line integrals, this f.dr, that dot product, I can see what the coordinates are of the things that I'm dotting, and therefore I know how to actually execute that dot product. That dot product, I can write it out in coordinates like that. Which is weird looking, but I mean, again, it's just notation. I'm just kind of writing down what the notation kind of suggests that I should. So that said, we've got ourselves an alternative notation now for vector line integrals. Instead of writing integral f.dr, you can write integral over the curve of p dx plus q dy plus r dz. Means basically the same thing. That makes sense? Everybody okay with that? I mean, it's just notation. Now, next question, why would you ever want to do such a thing? Right? And the answer is going to be that for our purposes in this class, you probably won't. It doesn't bias any. This is not a computational, win. This isn't any easier to compute than that is. They're literally the same thing, right? We don't have any existing convenient theorems for how to compute these, individual coordinate integrals. We just don't. So this doesn't bias anything. Why then am I showing it to you? Why am I wasting your time with this? And there's two reasons. One is kind of historical / cultural, I guess you might say. It turns out there is this thing called differential forms. This is a very, very powerful idea. This is the tool, one of the important tools that allowed for massive progress in how to understand vector calculus in sort of the early to middle 20th century. Extremely powerful ideas called differential forms, and it turns out they look pretty much like this. This is what we would call an integral of a differential one form. So now, what can you do with this, and why does it work so well? Well, this is well beyond the course, right? But it is extremely powerful, and again, you can solve problems using these as tools, and combined with other very sophisticated stuff that's way beyond what we can do in this class, to great effect. So anyway, there's something kind of cool about that, right? Even if we're not going to be able to do those cool things, knowing that those cool things are possible because of this notation, it's got to be worth something. The second reason you need to know this is that it is in common use, and you're going to see this in your engineering travels. Some people really like to use this notation. In some cases, they like to use it for excellent reasons. And in some cases, they like to use it because I'm not sure why. No particular reason, no particular advantage, but they still like to use it. So you're going to see this. And so the question you have to face is, okay, when I see this, what am I supposed to do with it? How am I supposed to make sense out of it? Right? And I suggest that you should do the following. When you see this, you should look at the dx, the dy, and the dz. Remind yourself that that is just an alternative notation for dr. Right? And that correspondingly, the p, q, and r, in other words, the integrands are just telling you what your vector field is. Right, so when you see one of these coordinate line integrals, weird construction, right? Integral over a curve that looks like a bunch of single variable integrals, but it's not, because it's an integral over a curve. This is just an alternative notation for a vector line integral, and the PQR are just telling you what your vector field is that you're doing a vector line integral. Is that cool? Everybody, you see what I'm talking about there? Okay. And then you can compute the corresponding vector line integral. Okay. Symmetry theorem. Does this look familiar, I hope? In fact, I have deliberately written this, laid out on the page, to look exactly like several other symmetry theorems that we've written down, specifically odd symmetry theorems. And it's because, morally speaking, the way you use it is just like the other odd symmetry theorems we've talked about. The reason it's true is just like the other odd symmetry theorems we've talked about. It's the same basic ideas as the odd symmetry theorem we talked about for single variable integrals, for double integrals, and for triple integrals. It's the same basic idea, just now instead for scalar line integrals. Same basic idea, though. If you have a domain that's symmetric over some line, and if you have an integrand that is odd, and you got to have both of these conditions, and it's got to be for the same line for both of those conditions, then the integral is zero by symmetry, and you drop your pen and walk away. Everybody happy with that? Okay. Works in 2 dimensions, works in 3 dimensions. Any context? The asterisk, the landmine on all of this is specifically, and you'll notice I underlined it here, this is specifically and only for scalar line integrals. If you are looking at a vector line integral, it does not work. There is no odd symmetry theorem for vector line integrals. It's not true. It doesn't work. It doesn't work at all. And it's a little surprising because, I mean, my gosh, odd. I mean, odd's a negative on the one side than is on the other. You would think of cancel. I mean, doesn't that just kind of automatically work? And the reason it does not is visible in this picture here. Keep in mind a vector line integral. We like to write it like this, but there's an alternative notation like this. And I'm actually going to think about this one here. If you look at the ds, I could argue that that little ds and this little ds are equal and opposite, right? They're reflections of each other. This is the same size as that. If I had an odd function, blah, 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 sure. I mean, you'd think that we could make an argument like that work. The problem is, if you look also here, we're going to need to involve those unit tangent vectors. And notice the unit tangent vectors, like so, they're not the same. The DS's are the same. The tangent vectors are not the same. And it's worse than just being not the same. They're also not negatives of each other either. They're not equal, they're not negatives, they're just different. And so the whole thing just crashes and burns, and it just doesn't work. Yeah?
They're not opposite of each other in any dimensions, like, can you cancel components?
Do what now?
Can you cancel components of them?
Components.
Yeah.
There is a different theorem that I'm not going to tell y'all because it's more trouble than it's worth. Said differently, you can get yourself into more trouble than you can get yourself out of. And depending on how you look, anyway, you can talk about something called a mirror symmetry theorem. It's not the same as an odd symmetry theorem, and there is a way to craft a mirror symmetry theorem that would be valid for vector line integrals. But there's a lot of ugly little details as to what is this mirror symmetry? What does that look like? And it's more complicated than we can really get into. Like I say, it's so kind of yes, right? So to your question, you can make a different theorem that would work, but it's not worth your trouble. Yeah. Is that satisfying?
Yep.
Okay, so as far as we're concerned in this course, if you're looking at a vector line integral, symmetry doesn't help you. Okay. All right. Okay, moving along. We only have a couple of minutes left here, but I want to say a few things about 6.2. So we're going to talk about Green's theorem next. Green's theorem is a very powerful theorem. It's a very sophisticated theorem. It is... let's see how to say this. It's mysteriously sophisticated and powerful. And there are some excellent ways to think about this. That it's a new way of thinking that is a little bit counterintuitive. And ultimately, again, very, very powerful. And we're going to be able to do great things with it. And furthermore, what we're going to see with Green's theorem is a lot like other powerful, sophisticated theorems that we're going to see throughout the rest of chapters 6 and 7. Y'all have probably heard of Gauss's divergence theorem, Stokes' curl theorem. Right, so those are all kind of in the same ballpark with Green's theorem. So I'm going to approach Green's theorem in a very particular way with the purpose in mind of setting up a point of view that will allow us to approach the divergence theorem and the curl theorem and some other related theorems kind of all in the same way. So there's a particular strategy that we're going to apply to be able to do this, and I just want to kind of start this abstract discussion of what is this strategy going to be, and we've got a couple of minutes. The first thing I'm going to talk about real quick is what do I mean by a quantity on areas. And this is ultimately not that big of a deal, but the idea is for every area, let's not worry about regularity issues. For any given region, any two-dimensional region, a quantity means you can give me a value corresponding to that region. So an easy example is mass. You give me a region, I can say, okay, here's how much mass is in that region. Bigger region, more mass. Littler region, less mass, probably. Depends on the density, right? But for any given region, there is a corresponding amount of mass. For any given region, there is a corresponding amount of area. So this is, again, what we mean by quantity. You give me a region, I give you a corresponding quantity, a value. Perimeter is going to be an interesting one. You give me a region, we can talk about what is the perimeter. Related idea, and here's where we'll call it for today, an accumulating quantity. Now, y'all have heard me say that a million times. The whole idea of an accumulating quantity is that the whole is the sum of the parts. Every integral we've ever written down, every integral you've ever written down in any previous calculus course, fundamentally, the quantity in question has the feature that the whole is the sum of the parts. That's what an integral does. It takes a whole, it chops it up into little pieces. You look at each individual piece, and then you add up over all the pieces. You capitalize on the fact that the whole is the sum of the parts. And all I'm doing here is making the observation that disjoint unions add. In other words, if I look at how much mass is in the green region, and if I look at how much mass is in this blue region, and then if I ask related, if I look at the union, if I look at the whole, is purple equal to green plus blue? Well, of course it is. That's how mass works. That's how population works. That's how area works. Right? Accumulating quantities, they're all over the place. There's a lot of great accumulating quantities, but not perimeter. Perimeter doesn't work because the perimeter of the left region and the perimeter of the right region, those simply do not give you the perimeter of the union. There's that extra stuff. Right? There's all this extra stuff in there, sort of on the shared border. There is more perimeter on the individual parts than there is perimeter for the whole. So not everything, very important to realize, not everything's an accumulating quantity. So when things are an accumulating quantity, we have a computational foot in the door that we otherwise don't normally have. And more cool stuff that we'll do with accumulating quantities on Wednesday. Y'all have a good rest of your day. See you later.